I want to go back to its relationship to the KdV equation. And I want you to try and tell us a bit more about this equation because it does show up a lot in your research and it kind of is the foundation of where you go afterwards. And I'm just curious for the KdV equation, what kind of special properties does it have? And how does one attempt to solve an equation like this?
Yeah, so after they found this property that you could have multiple solitary waves in a KdV solution, they at the time, in the 60s, the QFT was taking off, and there were all these particles that were people were talking about, um, and so they dubbed them solitons at that point, solitary wave plus on. They look like particles in the solution, sort of, because they keep their identity through interactions and everything. Um, so they called them solitons. And it was a few years later, in 1967, that Gardner, Green, Kruskal, and Miria were able to show that the KdV equation is what we now call an integrable equation, which means that it has infinitely many conserved quantities.
Integrable meaning infinitely many conserved quantities. Okay, so in physics, I learned that energy, for example, is conserved. Does that count as a conserved quantity?
Yeah, that's exactly one of these conserved quantities. So the original situation that you derive the KdV equation from is this fluid dynamical equation, right? So first off, you would expect physically that mass should be conserved, the mass of the water underneath the surface, right? So that is the first conserved quantity of the KdV equation, is the total mass of water under the curve is conserved. The next one is related to the momentum of the particles of the water particles. If you add up all the momentums, that should also be conserved, right? That's the second quantity that you can derive as a conserved quantity of the KdV equation. The third one is related to the energy in the wave, right? The energy of the mass moving in the wave. Um, that is the third conserved quantity. And then it turns out that there's an infinite number after that. Uh, there's just more and more quantities that you can calculate in the KdV equation that are conserved, just like those three we would expect physically to be conserved. There's infinitely more after that, and yeah,
It's a bit hard for me to conceptualize that I can have an infinite amount of conserved quantities. I mean, maybe I can say, okay, if momentum is mass times velocity, just take a simple example, and energy is mass times velocity squared, then is mass times velocity cubed and mass times velocity to the fourth, something like that conserved, or is it
it
completely different?
it is related to the if you look at the conserved quantities, mass, momentum, energy, they are related to you can compute them through powers of the surface. So there are higher and higher powers involved, and they literally do go up. Like energy is related to the square of the surface, and you keep going up. There's cubes and fourths and everything like that, and all of those are conserved. So that's what the hierarchy really is. That infinite hierarchy of conserved quantities is related to powers of uh, the surface height, essentially,
So I have
which
an
has
infinite
information
amount of
about.
conserved quantities on the KdV equation. That usually tells me that it should be easy to solve. Is that true in this case?
Yeah. In this case, yes, it is easy to solve. So what they also demonstrated is that this infinite hierarchy of conserved quantities was related to the fact that this KdV equation is fundamentally related to the Schrodinger equation. The Schrodinger equation from quantum mechanics. So a completely classical system. This is what really got me interested in the beginning. A completely classical system that's describing water waves is somehow fundamentally tied to quantum mechanics, right?
Which is
And
waves of probability or something unrelated to water.
yeah. So if we want to talk about the Schrodinger equation real quick, it is a an equation in quantum mechanics that describes the wave function, the evolution of the wave function, right? So the idea is in quantum mechanics, we have a particle, a quantum particle in a system, and what the system is a potential function as a function of space, right? So if we restrict ourselves to just one spatial variable, then at every point in space, you can say the system is exerting some potential energy on the particle, or is giving the particle some specific amount of potential energy at any given point. And then we ask, what are the dynamics? This is the same thing in classical mechanics. You can ask the same thing. So if the Schrodinger equation says that if the energy of the particle, or first let's restrict ourselves to potentials that they're defined over all of the real numbers. So it's like an infinite space potential function. But at infinity, it's going to be zero. So it's saying that there's nothing really going on at infinity. It's just empty space. But in the middle, we'll say the potential function dips a little bit. So if you think of this as like a roller coaster, then in the middle, you would kind of like, as you fall down one side, you would gain kinetic energy. And as you go back up the other side, you lose kinetic energy, right? So if we say there's a particle in there that has energy below zero, that means it has to be stuck somewhere in the middle, because kinetic energy can never be negative, at least classically, right? So you'd have a particle oscillating in the middle. We'd call that a bound state. In the Schrodinger equation, when you solve for the wave function, you find that the wave function is localized near that area where the potential is below the energy, right? And then out towards infinity, it dies off very quickly. It's allowed to leak a little bit outside of there. That's what quantum tunneling is all about. But it dies off very quickly, and the probability that you'd find it out at infinity is exponentially small. So these bound states can only exist at certain energy levels, right? This is kind of the fun, like the thing that everyone hears when they first hear about quantum mechanics is these discrete energy levels, like in the atom.
So if I solve the Schrodinger equation for the simplest system of I trap the particle in a box of really high potential energy, then the solutions end up being discrete in energy. That's the classic example, or
Right.
I shouldn't
Yeah.
say classic to be confused with classical, but it's the number one example,
Quintessential.
the quintessential
Yeah.
example you see in a
Yeah.
quantum mechanics course is you get discretized energy levels by solving the Schrodinger equation.
Right. And
Uh,
if you wanted to solve specifically for the energy levels of the hydrogen atom, you would just make that potential function the Coulomb potential, right, of the center of the central positive nucleus, right? And then you'd be modeling what the electron is doing outside of the nucleus. That's exactly how it works in for the hydrogen atom. So you get these discrete energy levels. And then because if we're thinking about potentials that go to zero at infinity, if we ever have energy higher than zero, it represents a particle that can escape to infinity, right? Or you could think of it as a particle that's coming in from infinity with like a fixed amount of kinetic energy. It's got a fixed speed. And then it comes and it speeds up a little bit as it goes down the dip, and then slows down as it goes up the other side, and then it continues on, right? That's what would happen classically. In quantum mechanics, you solve the partial differential equation of Schrodinger's equation, and it tells you that you actually will have, if you have a particle that's coming in with probability 1 from, let's say, negative infinity in x, in the spatial dimension, uh, there's probabilities that it will get transmitted through this potential, or reflected through this potential back towards minus infinity.
So classically, I only go through basically
Right.
because
Yeah.
I have enough energy to go down and then back up. But in
Right.
quantum mechanics, there's a chance that I actually go backwards.
Yeah. There's just a quantum mechanical probability. When you solve the equation, you find that there's always some probability that you'll reflect, you'll head backwards. Um, so this is basically what you do with the Schrodinger equation is you do these mathematical quantum experiments where you set up solutions to the Schrodinger equation. You ask, what is the probability of reflection? What's the probability of transmission? And for a bound state, you're usually interested in what energy that bound state occurs at. And then another thing that you could derive is called the norming constant, which is related to, I like to think of it as being related to where like the particle is most likely to be. So it kind of tells you where the wave function is localized. It's information about where the particle is kind of sitting. So that's all the information that you can derive from the Schrodinger equation: reflection coefficient, transmission coefficient, eigenvalues, and norming constants. Eigenvalues are the energy levels. So it turns out that what Kruskal, Green, who was it? Gardner, Green, Kruskal, and Muria did in 1967 was they showed that if you take your initial condition to be a potential in the Schrodinger equation, or rather minus the initial condition. If you take the negative of your initial condition for the KdV equation and you make it the potential in the Schrodinger equation, the eigenvalues, as you evolve your initial condition under the KdV equation, the eigenvalues of the Schrodinger equation don't change, and the reflection coefficient and the norming constants change in a very simple way, an incredibly simple way. And then if you had some process to reconstruct the potential of the Schrodinger equation for different types of spectral data, the reflection coefficient, the eigenvalues, and the norming constants, then you would have a solution method for the KdV equation, because you could start with your initial condition, negate it, find the eigenvalues under the Schrodinger equation and the reflection coefficient and the norming constants, and then evolve those under the simple time dynamics, and then reconstruct the potential and then renegate it at the end to get a solution to the KdV equation.
That is super interesting. So I want to solve a fluid dynamics problem. I say, I don't like to deal with fluids. Let me go to quantum mechanics. Okay.
Right. Yeah.
Quantum mechanics is going to be easier than fluid
So yeah,
dynamics.
so much easier, because the time dynamics just happen to be easier when you solve that problem, that quantum mechanical scattering problem. Yeah.
Right. And then I do a bunch of quantum mechanics. I solve the Schrodinger equation. And you mentioned the spectral data, which are kind of, let's say, the data to describe your potential and the reflection and the transmission and the norming constant. And then I somehow go back to fluid dynamics with this
Right.
information in mind. And that helps me solve the problem. My
Yeah.
question is, first of all, that's super fascinating. You mentioned that the KdV is nonlinear. Somehow I go to the Schrodinger equation, which is linear, and then I can actually learn a lot of things that can help me solve a nonlinear equation, which is the
Yeah.
KdV. So how can I think of that? What's the magic there? How's that happening?
So it's exactly like if anyone is familiar with the process for solving a linear PDE, um, like you've already mentioned it, you sort of decompose your initial condition into these harmonics, right? And the harmonics have simple time dynamics. And then you sum them back up at the end to find the solution. It's exactly analogous to that. It is like you start with your initial condition, you conduct your scattering problem, you do the simple time dynamics, and then of the scattering data, and then you reconstruct under what's known as an inverse scattering problem the potential at a later time. And that gives you your solution to the KdV equation.
Is this a common technique in solving partial differential equations, or is this particular to the KdV equation?
It's particular to the KdV equation and sort of its cousins in the nonlinear PDEs. These types of equations that have the infinite hierarchy of conserved quantities are rare overall in all possible nonlinear partial differential equations, but there are a lot of them still. So there's one called the nonlinear Schrodinger equation, which is interesting. It's interesting that it also has the Schrodinger equation. It's related to the Schrodinger equation. Um, the sine Gordon equation is one that has this property. And then the other two equations that I'm most familiar with are the intermediate long wave equation, which is just a mouthful, um, and the Benjamin Ono equation, which are sort of more direct cousins of the KdV equation because they also come from fluid dynamics, kind of a fluid dynamical situation.